Alright, so welcome to my inaugural video that I am creating, and we are currently in the unit of gravity, and we've just started to understand really the major equation of gravity that Newton came up with, and that is that the force of gravity is equal to big G times one mass times another mass, and all of that over the distance between them squared. Okay, so as we start to understand gravity, we need to understand exactly what this is telling us about the world around us. And one of the major issues that Newton had was with his explanation of the orbit of the moon. So he said if the moon is falling towards us, which, of course, gravity makes things fall towards us, then why didn't it hit the Earth a long time ago? So if we have, let's see if I can make this a different color. So we have the Earth. It's a nice circular Earth. And then we have the moon up here. And this is obviously not to scale, but we know that the moon travels in a nice circular orbit around the Earth. And we also know that the Earth exerts a force of gravity, and that force of gravity is going to be something that looks like that. We have the force of gravity, and this is the force of gravity between the Earth and the moon. So if this force is here, then why doesn't the moon just fall into the planet Earth? Well, we've learned that if you happen to have a velocity, if you're moving with some speed and that speed is directed out something like this, that's not a force now, that's velocity. So if you have a great enough velocity, then what you can do is you can end up missing the Earth as you are falling towards it. So the Earth's curvature is just so that you're moving fast enough that you keep missing the Earth. So we kind of want to know how fast you have to be going for the moon to be able to miss the Earth like this, and it's really far away. So the question that we want to answer is basically how fast? How fast does the moon have to go, okay, to stay in orbit? So if we have the moon now in orbit around the Earth, we know it moves in a circle. So let's backtrack a little bit, and let's see if I can get myself another. Well, I can extend the page. Okay, so we're going to come back to that problem, and let's just imagine now that we are just in the classroom, and I have that large lanyard that I wear with my keys. So here are my keys. There you go. That's a really nice key. There you go. All right, and it is on my lanyard. Okay, and I'm twirling this around, and it is moving that direction. That is your velocity. So what is making this move in a circle? If this whole thing were to continue to move, it would move in this really nice circle, not like I can draw one. So we have this really nice circle. Let's see if I can, maybe I can, there we go. That looks a little bit better. So what is causing this to move in a circle? Because we know that the law of inertia says that a motion of an object will stay like that even unless there's a force that's acting on it. So the velocity of this says that it should just move straight down. So why is it continually changing its motion? Well, we know that velocity is a vector. And because of that, we know that a vector has two different quantities. It has magnitude, which means just the number. Okay, I totally misspelled that. All right, magnitude. And then we have the direction. So if I told you that the velocity here of the keys moving around the circle was constant, then we would know that the magnitude is not changing. Okay, so we don't have to worry about the magnitude. But what we do have to worry about is the direction. So what if at some later time the keys were up here? Okay, there's my keys. And now it's moving like this. Same velocity, but now it's moving in a different direction. So we have a changing direction on our keys. Well, if that means that we have a changing direction, that means something about this velocity is changing. We have a change in our velocity over some elapsed period of time. Well, the velocity, the magnitude is not changing, but the direction is. But this right here, the change in velocity over the change in time, is exactly an acceleration. And we know that according to Newton's second law, that if you have an acceleration, you have to have a force that is there to create that acceleration. Okay? And this acceleration is basically in the same direction as the force because both of these are actually vectors. So what force is keeping this velocity in a circular motion, keeping these keys moving around in a circle? Well, it's just the force of tension along my lanyard or whatever string happens to be holding this in. We have a force here, and that force is tension. Well, that means that that tension has to be producing an acceleration that is going that direction. Well, that acceleration is known as a centripetal acceleration. Okay, centripetal means center seeking. Okay, center seeking, and this is not to be confused with something known as the centrifugal force, which I'll get into later. But the centrifugal force, if you ever heard of that, is actually not a real force. It is something that appears to happen when you are accelerating. So we'll come back to that. But the centripetal acceleration, the centripetal force, if we were to talk about it, is an actual force, and it's directed along the inside of the circle. It's always directed towards the center. It's center seeking. So we actually have an equation for the centripetal acceleration, and that is that centripetal acceleration is equal to the velocity squared, which we know that velocity isn't changing if it's constant around the circle, divided by the radius of the circle, or basically the distance between the center to the actual key, or whatever it is that's moving around in a circle. So if you have the centripetal acceleration and you plug it into this equation, then you can talk about a centripetal force. All right, so if that is the case, then let's go back to this situation right here where we have the Earth and the Moon. The Moon is basically taking the same place as the keys in our circular motion, right? It is moving in a circle. We know that there is a force that is directed towards the center, and that center is the Earth, basically, because we know the Moon is revolving around the Earth. It's in orbit. So that means that this force of gravity has to be considered a centripetal force. Or you can say that this force of gravity is actually creating a centripetal acceleration. Mass times the centripetal acceleration. So we need to understand what mass that we're talking about here. Well, if we go back down to our key demonstration, then the mass that we have here is the force exerted on a mass causes its acceleration. So the force is being exerted on the keys. So in this case, the mass here is the keys. So if we go back up, then the force that's being exerted is the force of exertion on the moon. So what we're dealing with here is the mass of the moon. And if we actually make this correct on this side, we would have the force, or excuse me, the force between Earth, that mass, and then the force of the moon. So what do you notice here? What do you notice here about the mass of the moon? Well, it's on both sides. So I'm going to write this out a little bit neater. So I'm going to create myself a new page. Remember that you can pause the video or rewind it or go back and take a look at anything that you need to in the video. So if we have that the force of gravity is equal to mass of the moon times its centripetal acceleration, then what we have is big G, the universal gravity constant, times the mass of Earth times the mass of the moon divided by the distance between the moon and the Earth squared. So distance between the moon and the Earth. This equals the mass of the moon multiplied by that centripetal acceleration. Well, the masses of the moon cancels out from both sides of the equation. So we're left with that big G times the mass of the Earth is equal to the distance between them squared. That equals the centripetal acceleration. But we have another formula for the centripetal acceleration. We know that the centripetal acceleration is equal to that velocity of the moon squared divided by the distance between the center and the object, here the moon, not squared, excuse me. Let me get rid of that. Okay. So v squared divided by r. So again, what you might notice is that we have r's on both sides. Now, they're not going to completely cancel out. We have one that cancels out here and one that cancels out here. So we actually still have that distance here. And it makes sense that the further you go out, the velocity goes down, right? So you don't have to move as fast as you go out. But also notice that the speed that you have to go has nothing to do with your mass. This is a recurring theme that we've been seeing, right? Is seeing that, hey, mass does not matter. So if we continue this out, we would have velocity squared is equal to big G, mass of the Earth, divided by the radius, the distance between them. And we can square root to actually get our final answer. And I just like switching colors. So V is equal to the square root of, putting everything in here, we would have 6.67 times 10 to the negative 11th kilograms. No, I always get that messed up. So meters cubed per kilogram second squared. That's big G. The mass of the Earth we know to be 5.97 times 10 to the negative, no, not negative, times 10 to the 24th. There we go, that's kilograms. And then we need to know the distance between them. And we actually do know that. That distance is 384 million meters. So that's 3.844 actually times 10 to the 8th meters. And when you plug all of that into your calculator, we figure out that it has to go 1,108 meters per second, or roughly 1 kilometer every second. Okay, so that's the speed that the moon has to go to stay in orbit. Okay, thanks for watching this video, and I hope that you got something out of it.